Okay. So we learned about two distributions so far. The first one is called Z distribution. This is when sigma is known. And we learned about T distribution when sigma is what? Unknown. How do you know whether sigma is known or not in a problem? When he says assume that population standard deviation is 10, for example, that means he's given you population standard deviation. But when he gives you a sample of size 13, has a mean of 5 and a standard deviation of 2, he's given you S, not sigma. So then it's a T distribution. We learned also that we use two tables. One is called table 4 for Z distribution, and another one is table 5 for T distribution. And these both distribution are used to test the mean, whether the mean is bigger than a number, smaller than a number, at least a number, less than or equal a number, etc. But what about if someone asks me to test the standard deviation? For example, guys, if you need to test this claim. Look at the sign here. This is not the mu, and this is not the p, not this one, and not that one. You learned how to work with mean and p. And for the sake of your test today, only mean and p. But what about if the claim is about testing the variation, the standard deviation? The standard deviation is a measure of variation. How much, just does data spread out from the mean? If someone asking me to test the claim that the standard deviation is more than 5, how do I do that? The Z test will not work. The T test will not work. So there must be a different test, for this. And there is a different distribution that we use to test the standard deviation. It's called chi-square distribution, which I'm going to show it to you in a second. They call it chi. I know someone mentioned that on Monday, and they write it like this: chi-square distribution. This is the chi-square distribution. And let me show you a visual of the chi-square distribution. Because it is a square, guys, it's positive, because when you square a number, it's always a positive. And here is how the distribution looks like. Watch. Just gonna bring the camera closer. Okay. It has degrees of freedom. Like for example, a degree of freedom of 2 means the sample size is 3, because 3 minus 1 is 2. And look, the smaller the sample size, the more skewed toward the right, the distribution. It is always a positive. As you notice, the distribution always starts at 0. Unlike the Z distribution or the T distribution, guys, where you can have a positive and negative, look, this can never be a chi-square distribution because it has negative values. A chi-square distribution has to start from 0 like this, and it's always skewed toward the right, something like that. So this is what a chi-square distribution. You can't have negative numbers at all. So all the values of the chi-squares are greater than or equal to 0. Usually you won't have 0, but they are always greater than or equal to 0. Look, with degrees of freedom of 5, look at the chi-square, it's skewed toward the right. Degrees of freedom of 10, look at the chi-square, it's skewed toward the right. 15, it's skewed toward the right. But look, when the sample size becomes 30 or more, look at the chi-square distribution. It will become almost bell-shaped and like very much, just symmetric. When the sample size is 30 or more, it will look like the normal distribution, but it doesn't equal to, it can't be less than 0. It's always a positive distribution. Total area under the curve, guys, is always equal to 1. The chi-square distribution is positively skewed. That means right skewed, and therefore the distribution is not symmetric. And the chi-square distribution is different from each number of degrees of freedom. As I told you, you don't get one curve for all distribution. It depends on the degrees of freedom. The larger the degrees of freedom, the more you make it look like symmetric, but it's most of the time, guys, it is a skewed, positively skewed distribution. As you can read here, as the degrees of freedom increase, the chi-square distribution approaches a normal distribution. So this is the distribution that we're going to be using to test the standard deviation. I'm going to show you how to do this using technology. So it will be on the calculator, just like we did with the previous sections. But I'm going to show you also there is a table called table 6 to find the critical values for the chi-square distribution. And let me show you how to do that. This is table 6. You can find all the tables, guys, when you go for tools for success, and you're going to see tables and formulas, and there are lists of tables. I will send you all the tables and formulas in the email if you just want to print them out and keep track of them. For example, let's say he gives you alpha 5% and he gives you a sample size of 17, and you need to test that sigma is greater than 5, and you have n equals 17 and alpha equals 0.05. How would you find the critical value? And the critical value, you see in the Z, the critical value is called ZC or Z0. And when you test the, when it is a T, it's called T0. And the critical value when you do a chi-square distribution is called chi-square sub-0. This is the critical value. The critical value is a number that splits up the rejection region from the non-rejection region. It's a divider between the rejection region of the null hypothesis and the non-rejection region of the null hypothesis. Now, how do you use the table? The table, they call it is a right table. So when you have a right tail test, you just can use the table as is. For example, if alpha is 0.07 and n is 17, let me see if 17 is there. Yes. Okay, if n is 17, what would be the degrees of freedom, guys? 17 minus 1 is what? 16. So you go just look at 16 right here and look for alpha 0.05 and scroll down until you get to 17. Then your critical value will be right here, 27.587. Let's say the sample size was 21. How would you find the critical value? To find the critical value, you have to subtract 1 from 21, so you get 20. I'm right here, guys. And then you need alpha, which is 0.05 in this case, and just read it from here. 31.410, that would be the critical value. Let's say the sample size was 4. I'm just trying to come up with values that show up on the table. And alpha is 0.05. So what would be the degree of freedom? Can you guys tell me? If the sample size is 4. Let me see in the chat. 3. Yeah. Look, guys. You look up the 3 right here and look for the 0.05 and you get it right there. And you'll see that you're going to use the 3 and 2 small sample size later. Now, what about if alpha is 10%? Well, if it is a 10%, you just look at the 10% right here. So this table, guys, is designed for right tail test. A student asked me last week, what is a right tail test? A right tail test is when the alternative hypotheses have the greater sign. When you have the greater sign, guys, and you are asked to find the critical value of the chi distribution, you just use the table as is. But what about if you have a left tail test? Let's do the scenario here. And then alpha is 5% and n is 17. Okay, so left tail test, alpha is 5% and n is 17. Any ideas, guys? How would I use this table? Remember, this table is designed to be a right tail table, but now I have a left tail test. What would you do? Let's listen to see what people say in the chat. Exactly. Here's what a student says. Instead of using the 5%, you use 95%. Because this is a right tail table and we're doing a left tail, you just do the total opposite of the 5%. So that yet you just use the 95%. And where is the 95% is right here, guys. Okay, so look, you use 100% minus 5%, which is 95%. And then this always minus 1, so 16. So look what you do, guys. This is the 16 right here, and then just go to 95%. And you get the critical value, which is 7.962. This is exactly correct. If alpha was 10%, guys, you just do 100% minus 10%, which is 90%. And look, this is the 90%, and 17 minus 1 is 16. And you just read the critical value from there. And how do you sketch the critical value, guys? Is just sketch it like that. This is the 0. This is the critical value. And we sketch it like this. This one will be the rejection region of the null hypothesis, and this will be the non-rejection region of the null hypothesis. So the critical value splits up the curve into two regions. In one region, you reject the null hypothesis. In the one toward the tails, we don't reject. This is when we don't reject the null hypothesis, and the regions where by the tails, where this is where we reject the null hypothesis, the smaller regions. Okay, what about if you have two tails, guys? Let's see if you can figure this out with me. And alpha is 0.05 and n is 17. How would you use, if you have two tails, you must have two critical values. One on the left and one on the right. They call him in the book a critical value left and critical value right. Would any student tell me, have an idea and how to find them using the table? Still, n is 17 and alpha is 0.05. Any ideas? So I'm going to project the table now. And what would you say, guys, how to find those values? What do we do? Is it just like the confidence interval now? You have two tails. What did you do with the confidence interval? Do you still remember, guys? When you do the inverse norm, what do we do? So alpha is 5% and n is 17. Of course, you need 16. Degrees of freedom will be 16, 17 minus 1. But how do we decide on those numbers right here? Just like we did with confidence interval. So what do we do? Yeah, subtract 100%. So here's what you can do, guys. I'm going to give it you the easy way. Take alpha and divide it by 2, which is 5%. Divided by 2 will be 2.5%. Watch, guys. Where is the 2.5%? It's right here. There are two values. Since the first value happened to be the first on the right, the second value will happen to be the first on the left always. If you have the second on the right, the second one will be the second on the left. So 0.025 and 16, you read the value will be what? 28.845. The second one, guys, it will be, oh, that's not the first. Sorry, that table is not complete. This is actually the third. There should be two more values, you know, just toward the end. So this happened to be the third from the right. The second value will happen to be the third from the left, and you just read it right here. And I'm going to show you the actual table, just 1 second. So you have two critical values. One is 7.564. You put it first, closer to 0. And the other one will be closer to the right tail, which is the 30.191. Let me show you the actual table, guys. Just 1 sec. Okay. So when testing the standard deviation, guys, you have three options. This, or just like in a regular hypothesis test. Or this one. Guys, you can never have less than in the null hypothesis. Don't make this mistake. I checked the practice of some students and they were mixing up, the null and the alternative. Don't mix up the null and the alternative. The null must have one of those signs. And the alternative must have one of those signs. You cannot switch them, guys, never. Or sigma, this is less than or equal to 5 or greater than 5. I'm just making up stuff. So these are the scenarios to set up the standard deviation, guys. Now, if he asks you to give me an estimate of the standard deviation, usually the sample standard deviation is called the point estimate of the population standard deviation. S, which is the sample standard deviation, is called the point estimate of the population standard deviation. Just like X bar is a point estimate of the population mean, and P hat is a point estimate of the population proportion P. So these are the three scenarios in any hypothesis test problem when you're testing the standard deviation. But sometimes, guys, instead of asking you to test the standard deviation, he asks you to test the variance. Testing the variance is the same thing as testing the population standard deviation. Variance is the square of the standard deviation. So you could also have the problem stated like this. Instead of sigma, you put sigma square. Sigma square is called variance. Equal and not equal. That's one scenario. Let's say if I square both sides, I get 25. Or the problem can be so what I'm saying, guys, this statement is exactly the same as this statement, because what I did here, I squared both sides. Square, 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 25. 5 square is 25 right here. Or sigma square is less than or equal to 25. Sigma square is greater than 25. These are all the scenarios. This is called, guys, a two-tail test. This is called the left tail test, and this is called the right tail test. If he asks you to test the standard deviation, you just put sigma. If he asks you to test the variance, you just put sigma square. It's the same thing. You're going to do the exactly same test. So what I'm going to do now, I'm going to show you a problem, guys. And then the one that you will have for the bonus assignment will be very much the same. So let me just do this problem. It's example 4 in section 7.5 on page 397, using a hypothesis test for the population variance. A dairy processing company claims that the variance of the amount of fat in the whole milk processed by the company is no more than 0.25. Can a student tell me what the sign no more, how would you express this sign?
Is it equal to or less than?
Exactly. You need to know that, guys. So no more than. That means where's the claim, guys, gonna be?
In the null hypothesis.
Exactly. And you guys, you can see the question. It says, can you reject the claim? They will never put the word reject the claim, you know, if the claim was not in the null hypothesis. As I told you before, guys, if the claim was in the alternative, they will ask you, can you support the claim? If the claim turns out in the null hypothesis, the author will ask you, can you reject the claim? Once you see the word reject, guys, be sure that the claim was in the null hypothesis. Okay, so, and it says the variance. The variance, guys, means sigma square. So variance, look, these are the keywords that I need. And no more than 0.25. And I think this is good enough for me to write the claim, the null and the alternative hypotheses. And would a student please tell me what the alternative is going to be? Yes?
Sigma squared and greater than?
Yep, that's it. Greater. You suspect this whole milk processed by the company is okay. And find that a random sample of 41 milk containers, so N is 41, milk containers, has a variance of 0.27. Okay, so you took a sample of 41 milk containers. This is from a sample, and you found that the variance was 0.27. The variance simple, guys, that we learned in chapter 2 is S squared, which is 0.27. If he says a sample standard deviation, you put S, but he says a variance, so S squared is 0.27. At alpha equals 0.05, is there enough evidence to reject the claim? Assume that the population is normally distributed. So alpha is 0.05. Can we reject the claim? Okay, let me show you the process, guys. Okay, let me see what we have in the chat here. Oh, we're squaring the standard deviation because he says it's variance. Once he says variance, it's a square. That's a good question. When he says, I'm giving you standard deviation, just leave it as S. But when he says variance, you just put S squared. All right. Step number 1, guys. State the null and the alternative hypothesis. You already done it. Identify the claim. You already identify the claim. Step number 2, guys, which is the test statistic. And please pay attention to it because you have to do this by hand. This is the formula. This is the formula. The calculator doesn't have a program to run this test for you guys. So you have to do it by hand, but I'm going to show you how to find the p-value using the calculator. So step number 2, it's very easy. Look how easy it is. Equal. Okay, help me out, guys. What's N?
41.
41 minus 1. What's S squared? It's given.
0.27.
Yeah. And what's sigma square? You just go always get it from the null hypothesis. This value you always get from the null hypothesis. That will be 0.25. And now let's do the math. Well, he's done already the math for me, so I'm just going to get it from the book, which is 43.2. Okay.
I have a question. So did he square S2 and
no, he says
2?
in the problem, he says the variance is 0.27. Once he says the variance, that you already have S squared.
Okay.
But if he says, that's a good question that you brought up. But if it says in the problem, the sample standard deviation is 0.3, and you need S squared here, you would need to square 0.3. So you make it 0.3 times 0.3. If he gives you the variance, you do nothing. If he gives you standard deviation, then you square each one of them.
Okay.
So this is 43.2. So that's step number 2. Step number 3, guys, which I'm going to show you how to do it. Find the p-value. We're going to do the p-value approach. p-value is going to be the area to the right of the test statistic, because we have a right tail test right here. And let's get the calculator ready. Just 1 second. So the p-value is the area to the right of the test statistic, because I have a right tail test. So I need to shade the area to the right of 43.2 that I got from step number 2. The area to the right, guys. So you start with 43.2. Remember, this curve goes indefinitely to the right, but never touches the x-axis. So what do you guys think that the upper limit would be right here? What would you put?
1,000,000?
1,000,000, yes, exactly. And then the degrees of freedom is n minus 1. So here's how you do it right here. Chi-square CDF, you put 43.2. I've just done that a second ago. 1,000,000, put whatever number you want, guys. Degrees of freedom, I have 41, so it will be 41 minus 1, guys, which is 40. And paste. And then if your calculator is an older one, it's gonna just give you chi-square CDF parentheses. So you enter 43.2, comma, 1,000,000, comma, 40, and then press enter. And here's the p-value, guys, which is 0.3362. So
I have a question.
Mm-hmm.
So I know we didn't get onto this part yet. Okay, but let's say it's left-tailed.
Oh yeah,
that-
I'm gonna show you the scenario. That's a good question, Abe.
Does that mean the lower limit will be 1,000,000 in that?
No, the lower limit will be 0, because the lower one will be 0 because it doesn't go beyond 0, not negative 1,000,000.
Oh, okay.
Remember in chapter 5, we do negative 1,000,000, positive 1,000,000, correct? But we don't have negative numbers here. So the lowest we can get to is what? 0. So we start at 0, but I'll show you examples. So chi-square CDF will be 43.2 lower limit. Let me write it down. Upper limit will be 1,000,000. Put trillion, guys. Put whatever number. Just make it big. And then degrees upper limit. And I think the one in the assignment is a right tail test. So just follow what I'm doing right here. And degrees of freedom, guys, is 40, which is degrees of freedom equals n minus 1. There you go. And you got p-value is 0.3362. And I'm done with technology. Once you guys get the p-value, you no longer need any technology, because that's the value. And if you Google and dig deep into how they figure out the efficacy, just of the vaccine to be 95% effective, just look for the p-value that they used and what alpha they used to compare it with. You're going to notice that the p-value is very, very small. And here, because the p-value is bigger than alpha, we fail to reject the null hypothesis. Okay, we fail to reject HO, guys. So how do you start? There is not enough evidence. That should help you for the test as well. When we say fail, we start with there is not enough evidence to at the 5% level of significance. Let me write it down. Two, support or reject. The claim is in HO.
Reject.
Reject, yes. There is not enough evidence to reject the claim. So the claim could be true, guys. When you cannot reject the claim, it is possible that the claim is true. We're not saying it is true, but you're saying it is possible. I cannot reject it. That's all I'm saying. I'm not accepting it, but I'm not rejecting it. That's the whole thing. So if this was a left tail test, let me show you what you asked me about, if it was something like that. And we're doing, just the variance. So, and let's say your chi-square turned out to be 70.53. And you want to run the calculator to find a p-value. Let me show you how to do this. So, well, actually, it will be, let's say, 10.53. So you just put the chi-square here, which is 10.53, and then you shade this area. Remember, this is a 0. So when you use your calculator, the chi-square CDF, you need a lower bound, which is a 0. The upper bound will be the 10.53. And let's say n was 25. So what would be the degrees of freedom here? So this is a lower bound. This is the upper bound. And this is the degrees of freedom. It will be 24. And then you can find the p-value this way.
What about a two-tailed?
Two-tail, you will have to split them up. So for two-tails test, and actually the handout that I put there just give you information about both of them. So you will have to do them, just in two separate ways. So you'll have one area that goes to the left and one area that goes to the right. The one that goes to the left will start with 0. The one that goes to the right, you'll just put a million, just toward the second end. So this is pretty much it. You're gonna get another example, guys, from me when you do the bonus assignment, different from this one. So just read it and just mimic what I did to get fully credit, just on the bonus assignments. And again, to find the p-value for a chi-square distribution, you press. Let me just show you again, guys. Just take a note or take a screenshot of what I'm doing. And you're going to see the screenshot in my handout as well. So I'll walk you through it before even I start chapter 8. You just press second, distribute, and go to chi-square CDF, press enter, lower bound, upper bound, degrees of freedom, paste, and then you should get the p-value. Now, if you guys like to solve this problem using the critical value approach, using the table that I just showed you, you could, but as I told you, I'm trying to be consistent since we've been using the p-value approach. Look what you can do. Instead of doing p-value in step number 3, we can do a critical value. This is a right tail test, guys. N is 41, so degrees of freedom is 40, and alpha is 0.05. Watch what we can do. Okay, 0.05 right here. And I need to 40. Let me see if I have a 40 here. Can you guys see the 40 for me? So what would be the value? What would be the critical value at 40? It is the fourth one, 43.773. Let me show you how we could have solved this problem. 43.773. Here's another step 3, using critical values. Scoot the curve. 43.773, just put it on the right. This is called the critical value chi-square 0. All right, what's the test statistic, guys? 43.2. If you place it on the number line here, would it be to the right of 43.773 or to the left of 43.773? Yes, right or left? It will be somewhere here. That's a 0. It's less, so it's gotta be here. This is the rejection region, guys, here. Always the area to the tail is the rejection region. And this is the non-rejection region. So since the chi-square fell in the area of non-rejection, then we make a decision to fail to reject the null hypothesis. If that's another way to do it, but I prefer that you just use the p-value. P-value more than alpha, fail to reject the null hypothesis. P-value is less than alpha, reject the null hypothesis. As simple as that, guys. All right, so you have several ways to do this.
Question, you said variance you don't need to square, but I know the example that we have or the problem we have does not state variance anywhere, so
So
we
then
do.
you have to square. Exactly, that's a good question. Let me show you another example here. When do you have to square? That's good you asked. Let me show you one where you squared. Yeah, this one I picked, we didn't square. Yeah, here it says has a variance, so you don't square. Oh, yes, right here. Watch. And these are all available, guys, in the book, so you just can see them. Okay, watch what it says here. A company claims that the standard deviation of the length of time it takes an incoming telephone call to be transferred to a correct office is less than 1.4 minutes. It didn't say variance, so it says standard deviation. So look what the author put, sigma, which is fine. Less than 1.4 minutes, that's the claim, and then greater than or equal to 1.4 minutes. A random sample of 25 incoming telephone calls has a standard deviation of 1.1 minutes. N is 25. It didn't say has a variance. It says has a standard deviation. So look what the author put. He put S equals 1.1 minutes. Did he put it somewhere? He didn't, but he should have put S. So S is 1.1. At alpha equals 10%, is there enough evidence to support the claim? See, when the claim is in the alternative, he'll ask you if you can support it. So he says degrees of freedom is 25. Let's find. Let me show you how he found chi-square. That's the formula. N is 25. Minus 1 is 24. And now S is squared. Now we need to square it because he gave me the standard deviation. And look what he did here. He did 1.1 squared divided by sigma squared. This value, guys, you get from the null hypothesis. You just go to the null hypothesis, which is 1.4, and square it. And look what he did here. He squared it. And then you get your test statistic. Okay. So you get 14.816. If you want to continue, he didn't do this using p-value, but if you want to continue, guys, finding this one using the p-value, the p-value is going to be the area to the left of 14.816 because it's a left tail test. So it's going to be this. That's chi-square. So this one, guys, you know, 0. So you go to chi-square CDF, and you put lower bound 0, upper bound 14.816, and then your degrees of freedom is 24, and then you can get the p-value, guys. That's how you do it. All right. So that concludes